All right, everybody, let's go ahead and get started. Let me probably turn the lights or get them fixed. There we go. All right. So let me go ahead and get the sign-in sheet started, and we'll sort of get back into our wonderful world of FEMAP. Real quick, I know you all have an exam due on Thursday. I don't know if you saw my email regarding my little hiccup on that one problem. So I'm just going to give everybody full credit on, let's say, number 9 and then number 8. Just do that one. Sound good? All right. Okay. Now, so last time we did sort of a full-blown start-to-finish FEMAP example to give you all kind of a flavor as to how this stuff works. And we did a cool little beam, and we got to deflect it and see it go like that, and got a nice little rainbow-colored contour and all that. And that's great and everything, but we're engineers, which means we actually need to start looking at these problems a little more applicably, shall I say. What I mean by that is, when you conduct a finite element analysis, what you're looking for is data. What is this stress? What is this deflection? What is this reaction? And what have you. So in that regard, we actually need to start looking at that. How do we actually run an analysis to get the data that we're after? Okay. So I want to sort of take it back a little bit and actually do a, I guess what you would call a more simple type of model. So I'd say I have here that we're going to analyze 2 problems today. That's probably not going to happen. We're probably only going to be able to analyze the truss. I mean, that's probably going to take us a fair amount of time because there's a couple things I want to show you in addition to just doing a truss analysis. But I'm using a truss because I think the resulting output is fairly simple. When we did that 3-dimensional beam last time, there was, if you took any one element, well, there's stresses in the x direction, stresses in the y direction, stresses in the z direction, displacements all different which ways, shear stresses, reactions. I mean, there's a lot of data that corresponded to just that one little problem. Okay? What we're going to do here is we're going to look at something like a truss because the output's pretty simple. I mean, when you look at a truss, you only get one output from each element, and that's the force inside the truss member. That's it, So we're going to do this to scale down our problem a little bit. I want to look at different means of creating geometry and different tools and tips and tricks that you might have at your disposal. And the big thing is I want to look at querying data. How do you actually get the info from the problem? Okay? So I put here 2 problems. Now, I wanted to look at these problems because this is stuff you all already know how to do. Like the problem on the left, that is a pretty basic, simple truss analysis problem. We won't need Poisson's ratio when we define our material. We'll actually, keep things a little more simple. We won't need a moment of, like if we do the truss, we won't need to define things in length and width and height. We won't need moments of inertia. All we need is to just plug in an area. So this model that we see is probably going to be a whole lot simpler to assess conceptually, but I just want to look at a couple different things. Okay, anybody have any questions? All right, one quick thing before we get started. So again, don't forget you all have an analysis project coming up. What I'd like to see you all do, especially the mechanical students, the masters in mechanical students, since you all have comprehensive projects and theses and whatnot coming up, is I'd like to see you all contacting your advisors or your professors in mechanical and saying, hey, this weird dude teaching finite elements, this Dr. Michelson jerk guy over here is giving us this project in this class. Is there anything that I can do for this class that's going to have some rigor to it, but at the same time that's going to start to get me towards a project or towards a thesis or give me some valuable experience that's going to help me later on down the road. I'm going to keep it pretty loose, but I'd like to see you all pitching some ideas to me. I've already had one student pitch an idea to me, and it's good to go. So, sound good? All right. If you haven't already done so, go ahead and open FEMAP. Let's see. Let me minimize this. Go ahead and open FEMAP. and we're going to do some modeling of this truss. Close the little tip thing. One of the things I'm going to do before we begin is I want you all to be able to read what you're about to see here in this message box. So what I'm going to do is I'm going to go to File, I think it's Preferences down here, and then where it says Messages, I'm going to make the message font something like, I don't know, 20, hit OK, and then I'm going to close the program and reopen it. And you should see the message box should be a whole lot bigger, so you all should be able to see what's going on down here. All right, turn the little tips off. We don't need that. All right, sound good? Okay, that's just for me. You all don't have to do all that. That's just because you all are sitting here staring at this screen, and I wanted you all to be able to see what's up here. All right, sound good? All right, so let's look at our problem. Okay, we're going to start off looking at this truss. And I'm going to do my best to try and keep with the numbering scheme that you see here so that you all kind of have an idea of what's going on. All right, so you notice this truss, it's got 6 joints. So real quick, before we apply boundary conditions, how big is the stiffness matrix? See if y'all remember. What's that? All right, 6 by 6, because it's a truss. How many degrees of freedom do each of those joints have? 2, because it can displace in the x direction and in the y direction. So how big is that stiffness matrix? 12 by 12. There you go. And how many elements do we have to deal with? We have to deal with 9, right? Right, makes sense. So 9 individual stiffness matrix feeding into an assembled 12 by 12, right? We'd have to knock out how many rows and columns? How many? How many rows and columns would we eliminate? Oh, man. It's been a while since we looked at this stuff, right? What's that? Not? Okay, I see where you would say 6, but 3 and 4 are not hinged. They're rollers. 4. We knock out 2 with joint number 1, and then 1 apiece with 3 and 4, right? Bringing it back, right? Okay, all right. So now that we went through that quiz and everything, let's actually get to doing some modeling. All right, so we got FEMAP open up. The first thing that we're going to do, and this is sort of the same thing we did last time, is we're going to create the geometry. Now, the geometry for this problem is fundamentally different than what we did last time. I mean, last time we created a 3-dimensional object inside FEMAP, an object that had length, width, and height. We're not going to do that here. Here, we're literally just going to draw a bunch of lines, and that's it. No extrusion, none of that, okay? Just length, width, and height. Well, that was last time. Now, for this, I guess you say there's only length. And then what we'll do to assign, I guess, volume to it is these members just have a length. We assign numerically an area. That's how you get that volume. All right, so the way I'm going to do that is let's go into geometry. Now, we kind of did this last time. When we did our surface, we created a surface based off 4 corners, and then we extruded. What I'm going to do here is I'm actually just going to start to locate points of interest, okay? Specifically, I'm going to locate 6 points, okay? So I've got 6 points. Maybe what I'll do to keep things simple is I'll say that joint number 1, that's my origin. That's 0, 0. So I'll go to geometry, point, and I'll say, okay, I got 0, 0, and then I hit enter, right? Remember how you hit enter, and then FEMAP keeps saying, hey, give me more, give me more, give me more, and then until you have to tell it, whoa, I'm done, okay? So we'll do 0, 0, and then we might do, okay, there's point 1 created, then we might do 15, 0, then we might do 30, 0, then we might do 45, 0, then we might do 15, comma 20, and then 30, comma 20, and then now I've got my 6 points, and I'm done. Any problem with that? What'd I do wrong? I did something wrong. What'd I do wrong? There you go. I did everything in feet just now. should have been, instead of 15 feet, it should have been 180 inches, right? So I did that wrong, okay? Well, no, okay, that's a good question. Do we need to start over right now? No, we don't, okay? And I'll tell you why. So, like I said at the very beginning, I said, well, what unit system does FEMAP use? The answer is, it doesn't use any units. You just need to be consistent, okay? Now, you as an analyst, it's very common that maybe you're analyzing some given part. You might be analyzing a part that, he designed. And he says, okay, I got this design. I'm going to give it to you to analyze. And he uses feet. And you go, I don't like feet. I want to get everything into inches because that's what I deal with. So how do you take this part in this geometry that we have defined, how do we take that and scale it to the unit system we like? That's where a unit conversion tool comes into place. There's a whole bunch of little widgets and tools and what have you in the background in this program. One that's really cool is the conversion tool. So if you go to, I believe it's geometry, or no, tools, and see where it says convert units. This is a really nifty tool, okay? Should look something like this. Everybody see that? Okay, all right. So if you notice, what you'll have here is there's 6 base factors, and then you can get a lot more specific as you go down. So to give you kind of an idea of how this works, let's say that your colleague who designed a part, let's say that they like to work in kips. But then you as the analyst go, in this scenario I've defined, let's say, no, I like to work in pounds. So what you might do is you might say, all right, I want you to multiply all of the corresponding force units by 1,000. Okay? And then what this tool will do is it'll not only do all the force units, but it'll convert everything else. So for instance, it might take pressures and multiply them by 1,000, because instead of being KSI, you want PSI. To give you kind of an idea, I drew this truss and these points in feet. I screwed up. They need to be in inches. So what do I need to multiply all my lengths by? 12. Okay, so watch what I'm going to do. I'm going to go in, and I'm going to enter 12, and I'm going to hit not OK, I'm going to hit calculate. Now, look what happens. It takes that base adjustment factor, and it adjusts everything else. So for instance, look what it did to area. It said take the area and multiply it by 144. Because it's not 12, it's 12 squared. Okay? Moments of inertia. You take moments of inertia and you multiply it by 20,736. Because it's taking feet to the fourth and essentially multiplying it to get inches to the fourth. What about right here? Damping and volume. Damping and volume multiply by 1728. 12 cubed. Here, when we're looking at damping, this damping ratio, it's not because it's an inverse relationship, it's 1 over 12. And see how it's taking into account everything else. Does that make sense? And you could get really fancy. You could say, let's take pounds per square foot and turn it into kips per square inch. I could throw another one in there, and it would figure out everything else. Okay? Now, what I'll do is I'll hit OK, and it'll say OK to recalculate factors prior to conversion. You hit OK. Now, what it just did, it might not seem like anything happened, but what it did is FEMAP just recalculated everything that we've defined up until now. Now, up until now, all we've defined are these 6 points. But I mean, if we had loads, if we had more geometry, if we had material properties, it would have done everything. Okay? Now, how do you know if what you just did is correctly, or was done correctly? Let me ask you this. All right, let's take this distance from here to here. In our appropriate unit system, what should this distance be from here to here? Wait, what? It's 15 feet. Converted, what should it be? 180. There we go, right? Everybody with me? That should be 180. Now, how do I tell that? How do I determine that? Anybody see the little ruler right here? Anybody see that? We're going to actually measure it. So this is actually a really nifty tool anytime you're doing an analysis. If you're working and you want to make sure you did something correctly, measuring is obviously the easiest way to do that. So if I select the little drop down, I mean I have distance between geometry. I only need to measure distance. Okay? Now there's a couple ways I can do that. I can sort of just eyeball it and kind of click right around here and kind of click right around here. If I wanted to be a little more exact, see this little box right here that says methods? It gives you a number of different ways that you can actually measure. You know, I can, between this location and this location, what have you. I'm going to do on point because I created points. I created them, so let's actually use them. So on point. So click that, and now it's actually, now look what it says up here. It says on point, and it says define location to measure from. Keep this straightforward. We are measuring from here to here. So what I'm going to do is I'm going to click, and see how the screen is now only finding the points. So I'll measure from here and see where it says point ID 1, hit enter, and then point ID 2, hit enter. Now, did anybody see what happened down here? Anybody see that? Something popped up. What happened? Let me close this box, and let me take this and stretch it up a little bit. Oh, okay. So what do we have? Measure distance. This is the coordinate system I'm in from x1, x2, x3, 2x1, 2x2, 2x3. So here's the coordinates of the first point. Here's the coordinates of the second point. It gives me the distance in the x, the distance in the y, the distance in the z, and then Pythagorean theorem to get the total distance. And it's exactly what it should be, right? 180 inches. Make sense? So that's how this tool works. Now, if I wanted, I could do this. I could, let me take that down a little bit. If I wanted, I could be a little more fast and loose with it. I could measure, and instead of going on point, I could just do locate, and I could say maybe kind of about right here, okay, to kind of about right here, and hit OK. Now what it was doing there on that second time is it was just finding points on the screen. It wasn't actually like snapping to the points I created. So it's not quite 0, 0, and it's not quite the location of that point, but it's pretty close. I mean, if you're just needing a rough estimate, you don't need to get as fancy with it. And you can see it's about 180. See that? Does that make sense? And you can get a little, you can get as fancy with it as you need. It's just a general idea. All right. Any question? Okay, all right. Let me drag this down a little bit. Let me hit Control A and sort of zoom in a little bit so I kind of have my points defined out. All right. So now we've got the points defined that define, where the truss joints are. We actually need to go and define the geometry. Now, again, we're not going to define a surface and extrude or define some volume. This is a truss. A truss is just a bunch of lines when you're thinking of an analytical model. So all I need is geometry, curve, line. And then all we have to do is just say, based on points down here. Because see, we could project points by actually trying to locate them on the screen, but why don't we define our line based off of the points that we've already created? So we'll go based off points. And this is about as simple as it gets. See where it says create line from points? Y'all see that? Like, what is element number 1? What is it, from 1 to 2? Why don't I just click joint 1, joint 2, hit OK. There you go. See how I'm doing that? Y'all want to go ahead and finish the truss out? So 2, 3, 3, 4, 5, 6. Bam, bam, enter. Click, click, enter. Click, click, enter. Now again, FEMAP is one of those programs that just like, hey, give me more, give me more. You have to tell it you're done. You can hit escape or hit cancel or hit the X. Either one's fine. And you should have a truss that looks something about like that. There you go. There you go. There you go. Not too bad, right? I'll give you all a minute. All right, everybody good? Okay, so our geometry is done. Now keep in mind, when you work in finite element, CAE environments like this, what we have done is create the geometry. We have not created the finite element model per se. We have to go through and create a material, create a property, assign that property to this geometry, mesh it, all of that stuff. This is just a bunch of lines. This doesn't mean anything until we assign that finite element data to this, okay? But what we can do is go ahead and actually start to constrain and load this model right now, okay? So what I'll do is keep in mind we're only working in this given space here. We need to create that load set and that constraint set. So we can say model load create and manage load set. We'll create a new one and call it applied loads. And hit OK. Done. And now FEMAP knows that we're working inside that first load set. See where it says the L1. Okay. Then we go model constraint, create and manage a constraint set. We'll call it, I don't know, boundary conditions. And now it knows that we are operating inside that first constraint set. It's the only one we've created. Make sense? Now, let's deal with the constraints first, or the boundary conditions. I think that's easier. So, let's talk about joint number 1. Joint number 1 is pinned, right? Which means it's restrained how? Like here's my coordinate system. Tell me what that means. X and Y. Okay. So here's what we're going to do. We're going to go to model, constraint, and then which one? You tell me, what do you think we need to do? On point, right? The last time when we had that beam, we fixed that entire surface, right? Now, the surface is grayed out because there's no surfaces, you know? So we're going to create a constraint on point, okay? So create a constraint on point. Now, this might seem like an odd question. How many joints in this truss are pinned? Just one, right? So what I'm going to do is I'm going to click point 1, hit OK. Now it says, okay, I've got a title, got whatever, let's call it pin support. All right. Now, okay. Now what I could do is I could say, all right, I could pin it, I could, prevent rotation or what have you, but maybe I want to be a little fancier with it. Maybe I'll look at arbitrary constraints in my coordinate system. Now, look what we have. Tx, Ty, Tz, Rx, Ry, Rz. What do you think the Tx, Ty, Tz means? Translation. That is preventing translation in the X, Y, and Z. What about the R's? Rotation. So we can prevent translation and rotation about all 3 coordinate systems. So you tell me, which ones do we need to check? Tx and Ty, right? Because the truss, we only consider translations in the X direction, translations in the Y direction. So these are the only ones that we need to check. Now, before I hit OK, here, I'll go ahead and check them. Before I hit OK, this is going to sound like a silly question. How many of these are there? 6, okay? Now, hit OK. Now, what happened? We see a little symbol here, but it says 12. Why does it say 12? It doesn't say 12, it says 1 and 2, because we restrained degree of freedom 1 and degree of freedom 2. It's Tx, Ty, Tz, Rx, Ry, Rz. It's 1, 2, 3, 4, 5, 6. You see what I mean? So it's basically saying we restrained all of them. Now keep in mind, again, FEMAP is one of those programs that's like, wait, give me more. I can't, give me another one. All right? So we've done our fixed support, or our pin supports. What about our rollers? Now, let me ask you this. We have a roller at 3. Do we have a roller at 4? Why do 2 separate boundary conditions? Why don't I just do all my rollers right now? So why don't I click this one and this one and just do the same thing to both of them? All right. Hit OK. We'll call this a roller support. Well, again, I want to be fancy with it. We'll do that arbitrary. Now, which one do I need to check? No, why? Why? Because it's the roller. It is free to translate it. In this direction, it's restrained in the Y. So before I hit OK, what's it going to say on each of those joints? 2. It's just going to have a 2. There you go. See? Not too bad, right? Pretty straightforward. Okay. That's our constraints, right? Are there any other ones? Am I missing anything? Sound good, right? Now, how many applied loads do we have? We have a 30 kip, a 30 kip, and a 10 kip, right? You tell me, how many different load definitions, though, should I do in FEMAP? I got 3 different loads. How many should I do? 2. I should just do the 30 kips at the same time, right? So what I'm going to do is, now let's do the loads. So I've got model, load, and then you tell me, what do I do? On point. Yeah, I'm not going to do it on a curve or on a surface. Now, let me ask you this. Is there any, why would I do a load on a curve? What about our next example? It's a beam, right? And beams have distributed loads. They have, triangular loads. So that's when we would do things like loads on curves. Make sense? So we'll do load on point. Now, we're doing the 30 kip loads. That means I need to select this one down here and this one up here. Okay? So this one down here, this one up here. Hit OK. Okay, now, give it a title. Maybe call it vertical loads, because those are the ones going down. Now, I've got force, moment, displacement, velocity, acceleration, all that stuff, fluid pressure. Which one do I need? Just the force, right? Components, I got Fx, Fy, and Fz. Which one am I going to enter in? Fy. And what number do I put in? Minus 30, right? Because it's going down. And hit OK. And then look what happened. Now I've got point loads applied to those joints going down, negative 30 on each joint. Okay? Make sense? All right, so negative 30 going down. I've got one more. I need to put one up here, right? So what was that on number 5? Hit OK. All right, we'll call this lateral load or horizontal load, whichever one you want. All right. Which one do I put in? Fx, Fy, Fz? Fx. And what number do I put in? Plus 10, right? So plus 10. And you don't have to put the plus. You can just put 10. And look what it did. Exactly the way it should look, right? Not too bad, right? Okay. All right. Are there any questions? Everybody good? All right. So again, though, I know it looks like a truss, and it's got point loads, and it's got boundary conditions and what have you, but right now it's not a finite element model for one big reason. What is this truss made out of? Are they aluminum, wood, popsicle sticks? steel? It doesn't know because we haven't assigned material properties and we haven't assigned a finite element mesh. It doesn't know if these need to be bar elements, beam elements, plate elements. It doesn't have any clue because we haven't done that yet. So if you hit run, it just go crazy on you, okay? Make sense? All right, so now we need to actually start doing some material properties. So we'll start off with the material. We'll create my favorite material, steel. Young's modulus was it right here. It's 29,000. Now, I could put in a Poisson's ratio, a shear modulus, all of that. I could do all that, but it won't matter, okay? The reason why is, go back to what does the stiffness matrix for a bar element or a truss element look like? It just has AE over L in it, right? The L is defined by the geometry, the A is defined by the member properties, and the E is the material properties. It doesn't need a Poisson's ratio or any of that, okay? So I'm leaving everything else blank, and I'm going to hit OK. And again, FEMAP is like, give me more, give me more, give me more. Tell it, shut up. I'm done. All right? I can be funny every now and then. All right. So we created a material, but again, we haven't created a property. Now, I'm going to show you all something. Just bear with me for a minute. Now, if I go into property, I might say, all right, it's going to be made out of steel, and then I need to pick an element type, right? So I go into element type. Now, it's a little more complicated than what we did last time because I got rods, tubes, bars, beams, links, DOF springs, spring dampers. It's a little more complicated, right? Now, you as the analyst, it's your responsibility to know which elements are applicable for which problems, okay? Now, you might not be, you all are in the learning stage. You all are still learning what finite element is, what finite element analysis is. This program natively uses the engine NX-Nastran, okay? But that doesn't help you all in selecting this. Now, you all are probably going to think this is silly. I mean, how many times have you ever nowadays run a computer program and actually used the help menu, Well, we're actually going to use the help menu. Now, I'm going to escape out of it. Well, maybe I'll leave it up for now. I'm actually going to go to help and actually go, if you look here, there's a number of help topics. I'm going to hit NX-Nastran, okay? Now, if I hit NX-Nastran, it's an HTML file. Maybe we'll do it in Google Chrome. Now, you should have something like this pop up. Does everybody have this? Bless you. Everybody have this? Okay, all right. So we're not going to get into all of this, okay? Because there's a lot going on. I know. But this is kind of the nuts and bolts and the how-to around how NX-Nastran works. NX-Nastran is that engine that actually processes the models that we create. Remember how you click that little analysis button and it's done? This is how that analysis engine works. It's a lot going into it, right? That's what we've been talking about all semester, the different types of elements, the different types of materials, and all of that stuff. That's what we've been doing all semester. Now, if you notice, there's a number of different guides. We're trying to pick what element would be appropriate. Which one do you think we need to use? Maybe this one right here, the element library reference. This lists all the different elements that are inside NX-Nastran. So let's go to element library reference. And keep in mind, if you're using ANSYS, ANSYS has one as well. If you're using Abacus, Abacus has one as well. All major finite element packages have a library of elements, and they will tell you how each of those elements were formulated and how they work, okay? For instance, let's see. Go down a little bit. Actually, let me download this and actually open it in Adobe, because I can pull the bookmarks a little easier. All right, here we go. Okay, so if you notice here, let me drag this on over to the side. If you notice here, we've got a number of different types of elements. Now, we have three-dimensional elements, two-dimensional elements, one-dimensional elements, zero-dimensional elements. Like, that might not make a whole lot of sense. Zero-dimensional elements are if you have a lumped quantity at a given point, like a lumped mass or something like that. That might be a zero-dimensional element. We're looking at trusses, right? So maybe a one-dimensional element, a line. A two-dimensional element might be a surface, you know, like what we numerically integrated and what have you. Three-dimensional would be like what we used on that last problem. Let's look at one-dimensional elements. I dropped that down. There's a number of different types. Remember the bar, the beam, the rod? That's what FEMAP was referring to. Let's look at a lot of these. Let's look at the bar, for instance. Now, in NX-Nastran, and then here you could, it starts to describe to you what that bar does. So I'm going to read it out directly. In NX-Nastran, a bar element is a general purpose beam that supports tension and compression, torsion, bending in two planes, so bending either this way or bending that way, and shear in two perpendicular planes, so either shearing this way or shearing this way. Okay? So that element can handle all of that different stuff. Could we use that to you know, run this? Yeah, but it would be like using a sledgehammer to staple your homework, you know, together. It's a little too much, you know what I mean? Too much specificity for this given element. It's probably not the right one for the job, okay? Let's see. Now, for those, here, let me point something out. For those of you who decide to take advanced stress analysis next spring, like you'll see something right here with the C-bar, the centroid, the gravity axis, and the shear center all coincide. We'll talk about stuff like that in advanced stress analysis. How do you compute the shear center of a section? For something that's doubly symmetric, it's a non-issue because the shear center and the centroid are in the same spot. But if you have something like a C shape, like a channel, you'll notice that the shear center is actually off the back of it a little bit. And there's a reason for that. It's all about the shear flow around the section. So that's sort of an advanced strength of materials concept. But, you know, take Engineering 670. We'll talk all about it. Now, that's the purpose of these types of references, is so that you as the engineer can understand, okay, am I using the right element for this job? It's not a matter of just making the picture look pretty. It's got to be right, too. I guarantee you, with enough time, you could come up with a pretty little rainbow contour plot. That doesn't mean the answer's right. You see what I mean? That's what this stuff is for. Now, if you do a little bit of research and actually look into this a little bit, and actually look at the rod element, the rod element is probably the one that makes the most sense, because a rod, the only thing that rods do in NX-Nastran is stretch and twist. That's it. Like if I took a C-rod element in NX-Nastran and tried to bend it, the program would shut down and say that it doesn't understand, okay? Whereas all we're doing to these elements are stretching them and twisting. We're not even twisting it, but it can handle that. The purpose is to use the right analysis tool for the right job. You see what I mean? We don't need to do a nonlinear time history analysis with geometric and material imperfections and all that if all we're trying to do is a plain truss analysis. Use the right tool for the right job. So going back to FEMAP, if I'm in that, what was I doing? I was going to model, property, and I was trying to figure out what element to use. In Nastran, probably the right one is that rod, just the rod. So we'll hit OK. We'll give it a title. We'll call it truss element. And then it starts asking for properties like A. Remember the torsional constant J, GJ from strength of materials, perimeter, some other stuff. We don't need to put in any of this stuff. All we really need is an area which is 6 square inches. Now, you could actually get a little fancy with it and specify that this element is in fact a cable. What that means is that a cable cannot support forces in compression. It can handle tensile forces all day long, but no compressive forces. So that's just analytically, that's what it's talking about. So I called it a truss element. We hit OK. And then again, FEMAP's like, give me more, give me more, give me more. Nope, I'm done. All right. I know I went off on a little bit of a tangent to create that property, but I really wanted to make a point, okay? Make sense? Again, you as the analyst need to know what you're doing. And if you don't know, ask. And by ask, look it up, you know. Make sense? Okay. Now, again, all we did is create a property. We did not assign that property to what we are seeing here. And by assigning it, it means we need to create a finite element mesh. Okay? Now, how'd that whole mesh control thing work? Remember, the more control you subject that mesh to, or sorry, up one, the more control you place that mesh under, the better it will come out, or the more it will come out the way you specified. If you just let FEMAP do what it wants to do, it'll come up with the mesh that might make sense, it might not. I mean, you have to understand the finite element method is meant to analyze complex stuff. It does the best it can, okay? And in many cases, it does a good job. But you all need to have the ability to restrict that mesh into a, a form that you want. Now, we've got a number of options: size at point, size along curve, Which one do we need to use? Well, no. We wouldn't use the size at point because we're not trying to mesh the points. That's a good point to bring up. Do you actually need to mesh points? Well, if you have a lumped element, like a lumped mass, yeah, you kind of do, okay? But what we're trying to do is figure out how many elements along a given curve. Does that make sense? Now, size along curve. Okay. Now, the first thing I'm going to do is it's asking for which curves do I need to mesh. Well, I need to mesh all of them, so why don't I just select all? Okay? Need to mesh all of them. Hit OK. And then now it's asking for the number of elements. Now, I'm going to ask this question in a little bit of I guess, a different fashion than I did before when we first started doing trusses. How many members are in this truss? 9. How many elements are in this truss? Before, we've been saying 9, right? But I could, if I wanted, I could say, let's say we're looking at this member. I could say for this truss member, give me 4 elements. An element from here to here, from here to here, from here to here, and from here to here. So that in the finite element land, I'm actually placing a node here, here, and here. Okay? And if you're doing like geometric nonlinearities and things like that, stuff like that's actually important, actually for a given member using multiple elements. For what we're doing, no big deal. So how many elements do I place along these curves for what we're doing? Well, but this, okay, so we need a total of 9 elements. You are correct. But along a given curve, like from here to here, how many elements do we need? 1, right? We only need 1 element from here to here. So we just hit 1 and hit OK. All right, and then it's like, give me more, give me more. So I got to tell it to stop, shut up. All right. Make sense? Okay. Yeah, if you're doing something like a 3D bridge analysis and you're trying to figure out how the bridge behaves when, it's curved and it's skewed and you're trying to place the wet concrete on there and you're looking at things like the cross frames and the diaphragms in there, yeah, you actually do need to use like 5 or 6 elements for those diaphragms and cross frames because that stuff gets complicated real quick, okay? But for this, no big deal. All right? Make sense? Okay, all right. So, last thing that we need to do, we actually need to mesh it. Again, we haven't actually assigned elements to this model. So we say, all right, go to mesh, mesh the geometry. What are we meshing? Are we meshing points or curves? The curves. We're actually meshing those lines. So mesh the curves. Which curves do we want to mesh? All of them. So select all, hit OK. Now it's asking for what property. What property do I want to assign? That truss element, right? That's where I created that rod with a 6 square inch area. Then hit OK. Then look what it said. 9 elements created. So 1 element per curve. I could have done 6 elements per curve and got 54 elements total, Make sense? All right. All right, now, last thing to do, now we can actually analyze it. Okay, so we'll go to Model, Analysis. We actually need to create an analysis set. So or wait, new. And again, we could get fancy with it, but we'll just do a static analysis. Call it, I don't know, run the model. You can call it whatever you want. It really doesn't matter. Hit OK. Then just hit OK. And that last screen that I kind of went through quickly, it's where you can kind of request different output. Like you can request the total energy in the system. You could probably get kind of fancy and actually request the stiffness matrix, the system matrix for the whole model. I mean, that's if you're really trying to delve into the models that you're running. Most of the time, you aren't going to have to worry about that. And then hit Analyze. Done. Not too bad, right? Okay, all right. Let me close that out, this little analysis monitor. We don't need that right now. Okay, so we have actually run the model. The model is run. Okay. Let's see what it looks like when it's deflected. Remember right here we have an undeformed view, and then we have that deformed view up here. Remember that? Right up there. Click the deformed view. And that's what it looks like deformed. Now it's taking those deformations and it's scaling them up quite a bit so that we can actually see what we're looking at. Okay, but in the end, there's the deformations. And if I wanted, I could create a little animation, or and it sort of goes through the displacement sort of from +1 to -1. That's why it's sort of popping back up as well. All right, make sense? Okay, so maybe a nice little contour, right? Ooh, it doesn't like that. Doesn't like that contour, right? Gets a little ticked off. Why is it getting ticked off? Why does it not like the contour? Well, the reason why is because the way FEMAP operates, the first thing it wants to plot is von Mises. This is just a bar. The only thing it has is a stress. So the reason FEMAP is getting pissed is because it's trying to plot von Mises stresses, and there aren't any. So it's saying no data available for post-processing. So hit OK, and it gets upset. All right, so how are we going to fix that? We can go to we can right-click, and you can find this either up top or in the dialog box that pops up. But you notice a couple of things that you see here. Okay, one of the things is visibility, and you can have a lot of fun with that, figuring out what you want to see and what have you. But I want to take a moment and look at this post data. Okay. Now, this box, there's a lot of stuff going on here. Okay. So the output sets, if I drop down, there's only one. It says NX Nastran case 1. The reason why is because we have only taken this model and run the analysis once. I could put different loads on this geometry and run it again. I could run it 846 times. And what it would do is it would report the data based on, okay, that first analysis job you run or that 18th job that you run. Which if you're in design mode and you're trying to design some bracket and look at different loads, that might be important, okay? So for what we're doing, we only have the model and the load, so there's only one case. Now, the deformed vector, it's deforming the vector based on the values according to total translation, okay? The contours, there's nothing there. That's why there's no colors. So if I drop down, there's a bunch of stuff that we could see, okay? Now, if you notice, there is no von Mises there. That's why it didn't understand what was going on, okay? But maybe what if I pick something else? Well, the contours should probably be based on the loads inside those members. When you do a truss analysis, what do you get? You get the reactions and then the forces inside each member. Maybe I should pick that one, 3036. Y'all see that? The rod axial force. The axial force inside those elements. Rod axial force, hit OK. Now do a contour view. Now it's giving us some data, right? Now, I want to look at some things. Look at the scale. It goes from a +30 to a minus 23.2. Which one has the positive 30? Is it this one right here? This one? All right. Now, you all are engineers. Does that value make any sense? Let's ask. Positive 30. What does that positive mean? Tension. Does it make sense that this member is experiencing 30 kips in tension? Let's go back to statics or structural analysis. Look at this and look at a method of joints analysis right here. Think about method of joints. I got 30 kips going down. What do I have to have inside member number 5? 30 kips going up, which that places member number 5 in tension, right? And how much is the load? 30 kips. So this should be 30 kips in tension. So if that didn't say 30 kips in tension, I'd have done something wrong, right? Make sense? The idea is that, you want to be able to gut check those values and make sure they make sense. All right? Now, make sense? You can have a little fun with it and look at different contours and different forces and what have you. Now, here's a question. How much force is in this member right here? No, this one. I mean, it's got some colored contour. It's like this, bluish purple, this diagonal on the very right. So what is that, about 9 something? Do you want to design a bridge that your grandma's going to travel over every day to get groceries based on about 9 something? Or do you actually want that number? I want to know how much force is inside that member so grandma doesn't fall in the river, right? The point is that you actually need numbers. You need data from this model. The rainbow contour is pretty and everything, but it doesn't give you acceptable values for design. You need something you can use, okay? So that's where querying comes in. We actually need to start getting some data from this model, okay? Now, one of the ways that you can get that, you can actually have a lot of fun with this to start looking at the results from your model, is this toolbar up here where it says list. You'll see this up here where it says list? Okay. Now, what this menu will do is literally what it says. It will list things about the file you're working on. It will list things about the geometry, things about the nodes, the elements, everything, what have you. Okay. Now, what we're interested in is we want to list the output. Okay. We ran the model. We want the results. Okay. Make sense? All right, so list output, and it gives you a bunch of different formats and tables and whatever. Let's just do a standard list, okay? Just keep it simple. All right, what output set are we going to look at? We're going to look at output set 1. There's only one there, okay? Hit OK. And now it's asking for what do we want? What data do we want? Look at some of this stuff you can get. Displacements, eigenvectors, which are the resulting displacements from a given mode shape or what have you. Load vectors, constraint forces, what have you. Right now, let's just look at displacements, okay? Let's just look at Nastran displacements. Let's give it a joint or a title. Let's call it displacement at the joints. Now, sort field. What do we want? Let's look at total translation. All right, hit OK. All right, what nodes do we want to list? What displacements do I want? Maybe all I want is the displacement on this node or this node. For what we're doing now, let's just keep it simple. Let's say we want all of them. Hit OK. Now, you all probably are able to see that a little better. Oh. All right. So, if you notice here in the message window, you all probably got a bunch of stuff that popped up, right? Let's see. So, let's look at this report. So, it's saying this is the version that we're using, format, sort by the title. Displacement at the joints. That's the title of the report I wanted it to generate. Output set. That we only did the one model. displacement vector. Now look, it's got 0.1, 0.4, 0.8, 0.6, 0.7, 0.2. We'll look at what that means here in a second. But what do we have here? We've got T1, T2, T3, R1, R2, R3, right? Now, why are all of these 0 over here on the right? Well, all of these are 0 because we're only dealing with displacements in the x direction and displacements in the y direction. That is a result of the type of analysis that we are running, a two-dimensional analysis considering only axial effects. Now we've got T1, which are displacements in the x direction, T2, which are displacements in the y direction. Why are some of those values 0? Those are where we restrained it. Those are the constraints. So this one is probably that joint on the left, but if you notice, some of these point IDs don't quite match the point numbers that we see here. And the reason why is a lot of times what FEMAP and many software packages will do, and I don't cover a lot of this because I think nowadays some of those computational issues aren't the biggest deal. It's not like we're dealing with things on the big floppy disks and, you know, having processors and finite element models that take weeks to run. If you open up any textbook on finite elements, you'll tend to find a chapter that talks about solution strategies and things like how to store the stiffness matrix so that you're using up less hard drive space, and how to number the nodes so that all the boundary conditions are on the end and it makes it easier for the program to eliminate the boundary conditions and what have you. Is that important stuff? Yeah, it's important, but I mean, I could run probably a 10,000 by 10,000 finite element model on this, on my phone, you know. So it's not as big of a deal nowadays, you know. So I just don't cover it, all right? So to sort of explain this a little bit, what I'm saying is FEMAP is sort of by default trying to renumber the nodes so that it gets the best solution strategy possible, which for something like this, it just does the problem like that. It really doesn't matter, all right? Now, if you notice here on the bottom, it's reporting like maximums and minimums for each joint and what have you. So I'll go ahead and close that. All right, let me drag this back down like that and do that. Okay, sound good? Now, that whole joint 1, joint 4, joint 7, that raises an interesting point, because when I query data, I got to know what I'm looking at. What, like, joint 4 is displacing whatever, node 4 is displacing whatever. Which one's node 4? I don't know. You know, maybe we actually need to start looking at labels. Okay, so one of the things that you can do is you can right-click to visibility, and there's a whole bunch of different things that we can turn on and off. Like if you notice, here it's got entity and here it's got labels. Like watch this. See where it says geometry, and see I've got these multiple options right here? What happens if I just turn the geometry off? Now it's just not, it didn't delete it, it just didn't show it. You see what I mean? Just not displaying it. Maybe I turn the loads off. Boop, the loads are gone. See what I mean? Maybe I turn the constraints off, you know, and now I'm just seeing the truss as is, right? You know, maybe I'll close this, maybe I'll put it back in that non-deformed shapes. Now all I'm seeing is the results from the truss analysis. If I go back to visibility, I go to labels, now I can actually see a couple things. Like watch what happens when I turn the node one on. Now look what it's doing. Look at that. 1, 2, and then it did 4, 6, 7, 8. So it's actually, the labels are corresponding to what we're actually seeing. Maybe what I'll do is also turn the element labels on. Maybe turn the node ones off for now. Hit done. Now what we're seeing is this is element number 1, element number 2, element number 3. If you drew your truss lines in a different order than what's on this screen, now you can correspond. You see what I mean? So now when I go to list and I go to output and I do another output list, but now what I say is, instead of looking at total translations, I'm looking at rod axial forces, and I say, all right, give me the rod forces inside those bars, and hit OK, do all the elements. Now, I've got this picture up here of the truss, and I go to my, let's see, right here, and I go to my element ID and axial forces. Now I can actually say, okay, element number 6 has got, what is it, negative 2.3 times 10 to the first, so about 23.2 kips in compression. That's element number 6. Which one's element number 6? That one's element number 6. You see what I mean? So now I can do that correspondence. So on a problem like this, yeah, it's pretty simple. What about that beam we did last time that had, what, like 2,500 elements or something like that? Something kind of ridiculous, you know? Now if you're trying to look at the element with the most stress, you can find it easily, okay? And now we have data. I can actually design that element for that force. Make sense? That's the whole point behind what I'm discussing today. You actually need that data, that hard data. Yeah, the contour is pretty, and it helps guide you towards the answers that you're looking for, but you are engineers. You can't design a bridge that prevents grandma from falling in the river based on about 9 kips. That don't work. You know, need a number. Need something to go off of. All right. Does that sound good? All right. Anybody have any questions? Okay. So it's about 6 o'clock, so I think I'm probably going to call it. One thing that you need to have a knack for when you do finite element analysis, and it sucks, it's just the way it is, but you kind of need to have a really good spatial understanding of things. You need to understand, you know, like the right-hand rule. Remember that right-hand rule, you know, like how vectors go, like the x-axis, y-axis go like that? That's, you know, your cross product and things like that. You need to understand orientation and the x, y, and z. That stuff's important because, you know, when you do a full-blown three-dimensional analysis, things like orientation matter. Like if you're doing a beam, you know, yeah, the beam goes from here to here, but is it facing this way? Is it facing this way? Is it facing that way? That stuff matters, okay? Those loads are applied. Which direction are they applied? That stuff matters. So next time, we're going to look at this beam analysis problem, and we're going to have to address some of those issues. And in addition, we got this triangular load. We need to address that. How can we apply that triangular load easily? Because if you look, there's no just triangular load option, but there are ways that we can discretize and use load surfacing techniques and meshing techniques to represent that load. So, you know, a couple different options for things we can do. Again, just more, you know, tricks of the trade for you all to be able to do these analyses. Sound good? That's all I got for you today. I will see you all on Thursday. And you all have a present for me on Thursday, right? Yep. A celebration of learning, an at-home party. All right. We'll see you.